I've trained thousands of technicians on effective diagnostic techniques since becoming a technical trainer in 2010. And I've noticed some of the things that the best diagnostic technicians do to make them successful in completing diagnostic jobs. And we're going to look into 5 areas that you can start improving in today to instantly make you better at automotive diagnostics. The first thing to take a look at is diagnostic process. Now, if you ask most people about what their diagnostic process is, the first thing they usually say is, well, we plug in the scan tool and read the fault codes. And then if you say, well, what about if it was a knocking noise from the rear, or what if it was a water leak or something like that, then that gets them thinking about what diagnostic process is. So we're quite passionate about diagnostic process at Mechanic Mindset, and we've called ours Fixed It. Now, each one of these letters stands for a step in the process. I'm not going to go through the whole thing today, but I'm going to take you through the main parts of it. Actually, you can download and print this poster in the link below. So in this process, the actual diagnostics doesn't start until here. There are actually 2 steps that we want to perform before we actually start ripping the car apart and, probing wires with our multimeter and things like that. Take this car here, for example. This is a crank no start, and before we actually start doing anything, we're going to want to collect as much information as possible. History, accidents, what else have they noticed? In fact, there's a lot of information that you can collect as soon as you start going out to that vehicle. For example, when you unlock and open the door, you might hear the fuel pump primes. Now you know that that part of the system is working. Even simply unlocking the door is telling you that a large portion of this vehicle system is operating as it should be. And then, of course, we're going to switch the ignition on and try and crank it over. So just the very act of turning it on and cranking it over is telling you that there's lots of things that are working. Take the rev counter, for example. If you notice the needle moves when you crank it, it shows us that not only is the engine speed sensor working, but the engine management system is putting that signal onto the CAN bus network, and that signal is making its way up to the instrument cluster here. Massive amount of information there. So after you've gone ahead and took the time to find all this evidence, you then need to sit down and put it all together. Okay, so the engine does crank, it's not starting, I've got a crankshaft sensor signal. What's happening with the fuel pressure? Well, I heard the fuel pump was working. Have we got pressure up at the rail? All of these little things, ultimately to get you to a point where you're going to make your first test. And hopefully it's in the right place. And as long as you do both of those tasks well, you're likely to get a really good starting point for diagnostics. Save loads of time. Check out this video here where we show you a little bit more about the Fixed It diagnostic process. The second thing for us to work on is everyone's favourite subject, electrical diagnostics. This is renowned to be everyone's biggest weak point when it comes to diagnostics. Now, I'll tell you one thing that I've noticed is the people who have got this mastered have the fundamentals absolutely nailed. So the real basics of electrics, that's all you need to know, and you need to be able to do that very well. So here's some tips to help you get running with electrical diagnostics. Firstly is how the multimeter is actually working. Now, the multimeter is a difference measuring tool. So when you put your multimeter on the battery, so we put this on the negative or ground, that's 0 volts on this lead. We put this onto the positive side, we've then got whatever the battery voltage is. So in this case, it's 14.2 volts because we've got a battery maintainer on there. So what the multimeter's doing is taking the difference between 2 points. 0 on this lead, 14.29 on this lead. That gives us a reading of 14.29 volts. Now that's really important to remember when you get onto measuring things like voltage drop. So another tip is to do all of your electrical testing with the circuit switched on, okay? If the circuit's not switched on, it's not loaded, and you're not going to get the accurate readings and potentially end up with a misdiagnosis. So here we've got a basic circuit. There's 6 volts coming out here, a switch, we've got our bulb, and then that comes down to the ground side here, okay? So we're going to put our black lead on the ground and do our measurements from here. So at the power supply here, we've got 5.64 volts, and at the actual bulb, we've got 5.45 volts, so a drop of 0.2. So what you can do is use the meter as a difference measuring tool, and you can see there we've got about 0.2 of a volt. That there is a voltage drop test. However, if the circuit's not switched on, it doesn't work. So that's how we test the live side. For the ground side, we test it in exactly the same way, except we're not looking for a positive voltage, i.e. 6 volts. We're looking for 0 volts. Okay, so ground is just the opposite of live. So if we go on there and we get 0 volts, we know we've got a good reading. Here's another tip. If you connect up to a lead and the numbers are floating around like they are there, that's nothing, okay? So nothing is different to 0 volts. You can see there that it's a solid 0. In fact, if we go back to the actual ground here, you'll notice that as we go along it, 0.016, 0.006, 0.004, all the way down to dead zeros. Okay, so you see that flat zeros there, that is our flat 0 volts, different to nothing. Okay, so now we've moved the switch over to the ground side. This is something that catches quite a lot of people out. With it switched off, look, we've got our 6 volts at the power supply. Of course, that's expected because it's a uninterrupted connection. However, on the ground side, we've still got 6 volts. Now remember, all this bulb is a small piece of wire, okay? And it's not been loaded at the minute, so all we've got is 6 volts of energy sat there waiting, okay? It's not until we turn the circuit on that we get our 0 volts ground on that side of the bulb. So remember, switch the circuit on before you do any testing. Do not disconnect and test, because that could mean that you might miss other types of faults in the circuit, which I'm going to show you now. As for testing for faults, remember the circuit needs to be switched on. Okay, so you can see here that we've got some green crusties in the circuit now. The bulb is on, but it's very, very dim. If we turn that circuit off, we can see that at the bulb, we've got 6 volts, okay? Remember, this is a 6 volt circuit, so that's good, right? However, watch what happens when we turn the circuit on. It drops to 2.6, okay? Again, voltage drop. So, I've moved the green crusties onto the ground side now, okay? Switched off, we've got 6 volts at the power supply. Switched on, 5.72, that's okay. That means that all this part of the circuit is okay. Now if we check the ground, we've got 6 volts switched off. Remember, we're not connected this side to the ground yet. Switch it on, we've now got 3 volts. That's not okay, it should be as close to 0 as possible. Regarding your voltage drop limits, it's generally accepted in the automotive trade to have a maximum of 0.5 volts drop along a piece of wire. So with this circuit here switched on, an acceptable amount would be 12 volts, having a 12.5 volt power supply, and on the ground side, a maximum of 0.5 volts. Now they're the general limits, but always just take them with a bit of logic. Sometimes you might have a reading of 0.6 volts, however, the system might still be working okay. Looking at the bigger picture, does this consumer have enough voltage for itself to do the job it needs to do, taking away the voltage that's been lost on the wires? Check out this short video where we look at testing electrical circuits with live and ground switching a little bit more. The third thing to look at is sensor circuits. Once you understand the basics of how a sensor circuit works, the majority of sensor diagnostics becomes very, very easy. In particular, we're going to look at the voltage divider circuit, and you really need to have your basic electrical fundamentals absolutely perfect before you can really understand how this thing works. However, I'm going to do my best to make it really, really easy. So if we draw this basic circuit here with 2 light bulbs, exactly the same, we've got 5 volts at this end, a ground at this end, both the light bulbs would be switched on. What do we have in the middle? We should expect roughly half the voltage, 2.5 volts. So you can see that we've got that similar circuit set up here, but we've got a 6 volt power supply. Both bulbs are connected in series. The bulbs are the same. In the middle here, we've got around about half. So sensor circuits are generally made up like this. However, all of this part is inside the control unit, and this part represents the sensor. So instead of a bulb, we have what's called a resistor, and you might have heard the term pull up and pull down resistor. If the resistor has 5 volts on this side of it, it's a pull up resistor. That's then our power supply down to our sensor, and in many cases this sensor will be some sort of variable resistor with a ground on the other side. However, what you will find is that most sensors actually take a ground path through the control unit itself because it's much cleaner and gives us a more accurate sensor signal. So in this case here, this is like a coolant temperature sensor. Of course, this signal here is going to change based on the coolant temperature. And how it does that is that as the temperature of the coolant or the sensor increases or decreases, the resistance value here changes. That means that the voltage on this line here is also going to change. Let me show you. So I'm going to switch out this bulb here. Remember, this bit here represents what's inside the control module. And we're going to connect this variable resistor. So now we switch the circuit on. We can see here that we've got a value of around 0 volts. So to increase and decrease that signal voltage, we of course change the resistance on the sensor, which is represented by this here, okay? So by dividing the circuit voltage with 2 resistances, we make it possible to have a point where the voltage varies based on whatever the sensor is giving us. So we've already established that the sensor has a 5 volt power supply, but we generally say that the sensor has a working range of between 0.5 volts and 4.5 volts. These values aren't set in stone, so they could be a bit wider than this, and of course that wouldn't be true if it was a 12 volt sensor. It would be much higher than that. But these are general values. So what we have on the sensor is a working range. And if this was a temperature sensor, we wouldn't expect it to go outside of these dotted lines. So if that signal did go outside of the range up to 5 volts, we would say that that signal was too high. Seen that fault code before? Sensor signal too high? Well, you may have also seen the fault code signal too low. Now that means that the sensor signal has gone down to around 0 volts. When you get a fault code that says circuit too high or circuit too low, they're generally electrical circuit faults. And they're sometimes accompanied with the message short circuit to positive or open circuit, or short to negative or open circuit. And sometimes you've got to think, well, why can't it tell the difference? Well, let's have a look at how these fault codes would occur. So we've got our sensor connected here, and you can see that the lowest we can get it to go is about 0.5 of a volt, and the highest around about 5.8, okay? Now, if we make an open circuit in this circuit here, did you see that there? It jumped up to 6 volts. So it essentially jumped from its upper range, crossed the line to that higher range where it's too high. So that's how the control unit knows that the circuit's open circuit. The only other way to get the circuit voltage over that line is to short it to positive, like this. So if we shorted that to positive, that line would then go up to around about 12 volts. It's too high. That's why it can't tell the difference between an open circuit or a short circuit to positive. Okay, so I'm going to demonstrate that to you here. We're going to go on that sensor signal for the fuel pressure sensor down here, and you can see there that we've got 2 volts, okay? Now, if I disconnect that sensor, you can see there that that signal has now gone up to 5 volts, okay? Now, there was a bit of a warning message in the dash there. We should now then have a fault code to go with that, which you can see there, look, fuel pressure, circuit high. On the other side of that then, we've got circuit voltage too low. Now, if we short that signal down to ground, you can see that it goes nearly all the way to 0. So that's your sensor circuit too low, you're short to ground. Now, the other type of fault code we've got is if the sensor is given us a signal that is out of range or is implausible. In that case, the control unit is looking that the signal stays within a tolerance of operation. So at any given operating temperature, engine speed, engine load, the signals of the engine management system should be within a certain range. So at the point that they go out of that range, we then get a fault code saying signal out of range or signal implausible. So take temperature sensors. If the car's been left in the workshop and it's all cold, all of the temperature sensors should pretty much read the ambient temperature of the workshop. If it's a bit warmer, then of course the temperature sensors should be a bit warmer. If they're up to temperature, then they should be much higher. Pressures, with the ignition on, most of your pressures should be reading atmospheric pressure, which is 0 bar for gauge pressure sensors, 1000 millibar or 1 bar for absolute pressure sensors. So here, look, we disconnected that sensor and you could see there that the pressure jumped right up, and that's not going to move now when we start the engine and rev it. So the readings may also correlate to the faults that you've got on the system. And we're going to take a look at how you can help with those types of fault codes in the next section. However, if you want to see a bit more about the voltage divider circuit, check out this video. The fourth thing that you need to work on is live data. Now, it's really important that you kind of get to know what to expect when it comes to live data. One of the biggest complaints that I get from technicians that I train is that, how do I know what it's supposed to be? No one tells us what it should be. You know, how do I know if that reading there is correct?
I understand nothing.
Now, there's no real good answer for that other than that you need to get to know it yourself and understand what kind of signals you should be seeing, what data you should be seeing on those similar types of engines, because they're all pretty similar. So a 2 litre petrol on an Audi, you're going to get similar readings to a 2 litre petrol on a BMW. That's kind of the general physics of it, if you like. So what I suggest you do is take the time to learn what good values look like when you're just doing your regular job. So maybe week 1, focus on air mass meter signals for all the different cars you work on. Week 2, take a look at the MAP, manifold absolute pressure sensors for all the different cars you work on. The week after that, have a look at fuel pressure, temperatures, exhaust pressures, and so on, until you start to understand what those values should be on a good working car. The other thing that you're going to want to do is have a look at that data under different operating conditions. So what does it look like with the ignition on? What does it look like when it's cranking? What about when it's idling? What about when I rev it up and take my foot off the accelerator? What happens to that signal? And you're not going to have to take hours and hours out of your work schedule to do this. If you've already got the tool plugged in for a diagnosis on a different problem or a service or something like that, just take 1 minute, 2 minutes just to have a quick look at it, store it in the memory bank, and it will pay you back later, I guarantee it. So we're trying to build a library of known good data inside Mechanic Mindset so that if you are stuck, you can go and check it out, see if it correlates to what you've got. It's all included in the Diagnostic Coach program, and you can get your first month free using the coupon code MONTH. Go and check it out. So the fifth thing that you need to work on is everyone's favourite, wiring diagrams. Possibly the #1 roadblock to doing better and successful diagnostics quickly is getting hold of good information. After that would be interpreting it properly. Now, if you really get to learn and understand wiring diagrams, you're actually understanding how the vehicles work and operate, how these manufacturers put these systems together, because there's only so many ways you can achieve the outcomes of what we're doing here. So for the times when you can't get the wiring diagrams, you may already have enough knowledge to try and work out the system and test it properly yourself. So I'm going to show you a few tips in a minute to get the most out of these. However, Personally, I prefer using OEM wiring diagrams where possible. You tend to get a lot more information from the manufacturer, so I like to use AllData. That is a professional site. I think in the US you can actually get a hobbyist version of it and get individual diagrams. There's also a site called eManual. I'll leave a link for that down below, and you can get one-off OEM manufacturing diagrams from them for quite a reasonable price. Otherwise, you're looking at generic systems like Autodata or Haynes or Tech for Tex. Now, those systems are really good. The diagrams are generally very generic, so every time you look at a diagram, it's going to look the same. However, they do tend to lack important information like wiring colours, wire sizes, whether the wires are signal, a power or ground, which you often get on the manufacturer diagram. So anyway, let's have a look at some things you can do. Okay, so the first thing you want to do when it comes to diagrams is basically highlight the things that are definitely true. So for example, identifying power supplies and grounds. Now you can see down here that all of these blue parts are connected to ground. So we'll just put GND there for ground. So all of these blue ones here are connected directly to ground. Okay, that is a fact. Okay, so what you can then do is follow them all the way up. This is just a junction box here, so that ground is going to go all the way up here into this junction box over to this relay. Now here's one to not get tripped up by, is that on a switch, it's easy to say it, but when you're actually reading the diagram, it's easy to mess up, especially if you're testing the circuit with it switched off. It might be live on the other side there, okay? So remember what we looked at in our fundamentals earlier? Make sure you're testing it switched on. So of course, if that's switched on, then that side there is going to be a ground as well, okay? Then you've got the powers, okay? So if you've got a fuse on a diagram, fuses are always supplied by power, okay? Live voltage. So you can then follow those across, and then you've got a good reliable diagram to go back onto for your testing, okay? When it comes to components like actuators, we've got this motor here, we've got a relay coil just up there. It's always going to be a power one side and a ground the other, okay? So if you can identify at least one side of that circuit as being a power, the other side of it has to be a ground when it's switched on. Remember, that's the key thing, when it's switched on, because you can see here now this goes down to a switch. Now this is a Japanese diagram from a Suzuki, I believe, and they've got a lot of these switch types here. It's not very common for the diagrams I'm used to reading. However, it's basically a function switch, okay? So what you can do is just try and work out what it's actually trying to do. So we've got the different positions for the switch there. This is like a rotary type switch, so as you turn the switch, it's going to connect the dots of these different columns there, okay? So with this being the washer pump here, that you can see that when we go to wash, it actually connects these two up, which is giving us a path through the switch to ground, okay? So that's the ground path for the washer. And if you were diagnosing the washer pump, that's what you would have to try and work out before you could go and kind of test it accurately. So when it comes to looking for sensor signals and stuff like that, as I said, the manufacturer's diagrams generally have some information on there. But what you can see here for this position sensor, we've got a wire coming here. We've got a bit of a diagram in the middle here with a resistor and a pointy bit on it. So that pointy bit is likely going to be the bit that moves and gives us the sensor signal coming out of here, okay? The other thing with the BMW diagrams is they have this code on all of the wires. See this A, SAGR, R, SAGR, U, 5 volts. Well, those are codes for the wires, and they give a good indication of what that wire might be. So for example, they use U for power supplies, they use M for grounds, they use A for analog type signals, They might use T for timed quick on and off signals like pulse width modulation, and a host of other different codes too. Now, if you don't have any codes, sometimes you can use the actual wire thicknesses. So if you've got a module that's got, lots of different wires on it, generally power supplies and grounds for actuators will be slightly thicker than the power supplies and grounds for sensors. So if we look here, the pressure controller for the EGR valve has a 0.75 gauge wire, yet the sensor has a 0.35 gauge wire. Other than that, you could use the power of elimination, plus all of the other things you've learned about how these systems work to identify which wire might be which during testing. If you want to take your diagnostics to the next level, download our new mobile phone app and sign up at mechanicmindset.com today. Use the code YouTube to get your first month of Diagnostic Coach absolutely free.